So if you Google the definition of temperature, it gives you something like a degree of hotness or coldness, which is so useless. So if you go back and you add science to the end of your Google search, you usually get something like this. Temperature reflects the average kinetic energy of colliding and vibrating molecules, which I mean is better. Temperature has something to do with kinetic energy. And I feel like this is the one you learn in 8th grade and just stick it in your head. This works with our greatest physics equation of all time, right? PV equals nRT, of course. If you have a box and inside is a gas, if you heat up the gas inside that box, it's going to start moving faster and colliding against the walls. And since it's PV equals nRT, the pressure or the volume has to go up. And since the volume can't go up because it's in a box, the pressure goes up. That makes sense. So temperature must have something to do with kinetic energy. But where does that come from? So imagine you have a gas and you've trapped it so that it can only move in one dimension, like in a little tubey like this. And that's not that crazy. You could do that with a magnetic field or something, like really restrict the motion of some charged particles so they can only bounce back and forth in some, like, such a thin volume that it's just one dimension. And each particle inside this little tubey will be moving with some velocity, which will have a characteristic length that's however long it goes before it collides with something within some characteristic time. So we can think about the momentum of, I should draw a little eye for like each little particle. We can think about the momentum of each particle, which will be the mass times the velocity here, which we know is going to be mass times our characteristic length over our time. And then we can think about Newton's second law, which says that a force is equal to a change in momentum over a change in time. So we have our momentum here. We can just take the derivative and we get ml over t squared. We don't want time though. We're trying to get this thing to be a relationship with velocity. So let's replace our t squared with a v squared. So this will turn into mv squared over L. And if we want to move this into 3D, so our little tubey turns into I'm so good at drawing boxes. That's so good. This will just turn into the force in 3 dimensions is mv squared over 3L because it's 3 dimensions that it can move in. So next we can think about what the force of one of these particles does to like the pressure in the box, because these are going to be bouncing against the walls, and pressure is of course force per unit area. Although maybe the pressure due to one particle bouncing off the box doesn't make sense, so let's just say all of the particles bouncing off the box, so this is n, our just number density, and then 1 over area is going to be our little length here over the volume of the box times our force. But let's rearrange this. So we have pressure equals NLF over V. What we can do is bring the V over and we get PV equals NLF, where, you know, this is going to be our force. However, we can use the ideal gas law, the greatest physics equation of all time, where PV equals nRT, baby. Except we have a big N here and a little n here. So let's use the other version where PV equals big N, Boltzmann's constant, T. Okay, so now we know that PV equal to this and PV is equal to this. So we can set them together and we get that KBT is equal to L times MIVI squared. Oh, no. It's not M's I's and V's I's. Let's assume all these are the same mass, and instead of one velocity, we're going to take the average velocity of these particles. So it's going to be V squared over 3L. So these L's will cancel, and we get 3 Boltzmann's constant T, which is the temperature, is equal to mv squared. And this almost looks like kinetic energy, right? Kinetic energy is 1/2 mv squared. So if we multiply both sides by 1/2. We get 3/2 Boltzmann's constant times temperature is equal to 1/2 mv squared, which is equal to the kinetic energy. So here we see that kinetic energy goes as temperature. We freaking did it, guys. This is where this comes from. Okay, great. So we can one-to-one link velocity of atoms and molecules to the temperature of those atoms and molecules. We did it. Except, listen, I get it though. Everyone watching this channel is, of course, you have your scientist brain on, and you're thinking, what you just did is for an ideal gas. Like, surely that doesn't work for a solid or a liquid. Like, imagine a glass of ice water. The temperature of the ice, the temperature of the water is the same. And if temperature is one-to-one directly related to kinetic energy, it would mean that the energy of the water trapped in the ice is the same as the water trapped in the water. And that just doesn't make sense. But like, I hear you. Like, let's just leave the idea that this only works for an ideal gas, like in a little box at standard temperature and pressure, and just shove it over here. And we'll open that box later, but not right now. You can one-to-one temperature to kinetic energy. It makes perfect sense. And that's why temperature, of course, has units of energy. Temperature doesn't have units of energy. Temperature is a scale, right? It's not one-to-one related to kinetic energy. You have that sneaky little Boltzmann's constant right there. We had 3/2 Boltzmann's constant times temperature is equal to 1/2 mv squared, which is just kinetic energy, which of course is units of energy, which is joules. Boltzmann's constant has units of joules per Kelvin, or like whatever temperature scale you're using. That was a double joke though about temperature not having units of energy, because in some fields of physics, like high energy astrophysics or particle physics, people talk about the temperature of things in electron volts, which is a unit of energy. So they have this just defined unit of whatever kelvins. They're just like, 4 GeV temperature, which is, again, fine, because there is this relationship. Temperature is a scale. It doesn't really have units. Like, yes, you have Kelvin, but it is a scale. It is a range. The units on temperature are associated with Boltzmann's constants. That's where the units are. So you can equate temperature to kinetic energy. They do when they talk about electron volts. But I do think it's a little confusing because temperature is not the thing. I had a little demo. Hang on, I'll go get it. So you've probably seen this before, but I have these two plates that are of different materials. One of them I'm holding in my hand and it's cold, and this one is just like it feels room temperature. And we were talking about how temperature is not really the thing that exchanges energy in a situation when like you stick an ice cube outside on a hot summer day. It's not the only thing, at least. So something else that matters, heat capacity, the environment. So you'll see it with this demo. I have two almost the same size ice cubes, and I'll put them on and we'll just watch them melt back there, okay? So I will lean out of the way periodically so you can see, but the one closest to the bookshelf has a heat capacity that is allowing it to extract heat very rapidly from that ice cube. You can see it's already melting. Can you see it? Oh yeah, you can see it. It's even moving around back there. It's already melting much more quickly. While the one that's furthest from the bookshelf, closest to Arthur, right there, is not melting nearly as much. I'm in a room that is just one temperature. It's not the temperature of the room that is melting these ice cubes. It's the heat capacity of the thing they're sitting on, in addition to like the collision of air molecules with the ice. And that's the interesting thing about temperature and heat. A high temperature doesn't necessarily mean a high heat capacity. The famous example is in fluorescent light bulbs. Like the electrons bouncing around inside there are at a crazy high temperature, like 5,000 Fahrenheit. But when you touch a light bulb, it's of course kind of hot, but it's like 200 degrees Fahrenheit. And the reason is that the number density of electrons, even though they're very hot, is just too small to heat up that glass bulb. So high temperature doesn't necessarily mean high heat. How are we doing? All right, so maybe we'll check back in on these later. Another interesting thing about heat capacity is that if something has a large volume and a large heat capacity, meaning you have to put a lot of heat into it to raise the temperature of that, it's called like a heat reservoir. Like, think of the ocean. If you are standing on a boat because you're like wealthy and you're having a fun vacation and you're having your morning coffee and you throw the coffee into the ocean, like according to thermodynamics, the heat from the warmer body, which is the coffee, will move to the cooler body, which is the ocean, and they will meet at some temperature. So that coffee will add energy to the ocean. But it's not like you're going to burn yourself sticking your foot into the ocean, because the ocean is freaking huge. Right? That's actually why climate change is so scary. People used to deny climate change, but now they're just like, it's not so bad. The ocean's only 1 degree hotter. And it's just like, do you realize how much energy it takes to raise an entire ocean 1 degree? That's so much energy, which, will now turn into hurricanes and shit. It's terrifying that we have raised the temperature of the ocean. We have shoved so much energy into the ocean that is just gonna slam back into us. But anyway, let's do an aside. Thermometers, right? So if temperature is a measure of kinetic energy, does that mean that thermometers measure velocity? Does that make sense to you? I don't have any thermometers like this that you would put in your mouth. I don't know if they even make those anymore. I would love to have a mercury thermometer. That would be so cool. But this is just, they have like an alcohol liquid that they use now. This is a candy thermometer. You can stick it in boiling sugar. So these work by like PV equals nRT, baby, right? This is a vacuum. So you stick this in a hot thing, the temperature of this liquid goes up, which means the volume increases and it rises up till it tells you what temperature is. So this has been calibrated with a very specific volume, like there's a very specific circumference this is allowed to move so that you can accurately read temperature it looks like plus or minus 3 degrees Fahrenheit. This type of thermometer was invented in like 1612, and I have a lovely picture where you would stick a glass bulb in your mouth, which would heat up and then liquid would draw up. One thing that's really interesting when you're reading the history of science is realizing how important calibrated measurement devices are. Before, no one could agree on what temperature water boiled at. And you get a device like a thermometer and you're like, okay, I'm just going to make 10 of these. They're all going to be the same. We can all measure it and we can all come to an agreement. And the development of the thermometer is when you start getting like all of these different temperature scales. But the thing about temperature is that because of the zeroth law of thermodynamics, all scales of temperature have to be equivalent to each other. You have to be able to move from one to the other because it is just a scale. It's just a measure of energy. So it doesn't matter what scale you use. You're still going to get the same answer as long as you know your conversion. But imagine how important this is. If you are writing down your science and you're saying, I observed this chemical reaction at this temperature, or you're designing your steam engine and you can just tell everybody, like, this is the optimum temperature to operate this at. Here's a thermometer. Make sure you measure it. It's really interesting. Thermometers are very cool, but the whole temperature velocity thing was an example with an ideal gas, but that's not what's happening here. This is a liquid. I'm glad you brought that up. Does our little velocity goes as temperature little scale thing work for liquids? That's a great question. All right, let me drop some knowledge on you, okay? Not everything is an ideal gas, actually. I mean, if you're dealing with gas, most of the time you can just call it an ideal gas and you'll get a pretty good answer. Like, you'll be in the ballpark. You'll hit the backboard. It's going to be fine. Sports. But a solid, a liquid. It's not an ideal gas. The whole kinetic energy goes as temperature is extremely complicated by degrees of freedom. We saw that with our 1D box. When you constrain the movement of your gas to 1D, the kinetic energy goes as 1/2 Boltzmann's constant times T. And when you add the volume of the box, so now you have 3 degrees of freedom. You can move in the X, the Y, or the Z direction. The kinetic energy goes as 3/2 Boltzmann's constant. So you add another 1/2 kBT for each degree of freedom. But that is for a monoatomic ideal gas. What about a diatomic gas? There's more degrees of freedom. A diatomic gas would be like N2 or O2. You have 2 little guys stuck together. Yeah, they can move in the X, the Y, or the Z direction, but they're also going to be moving amongst themselves. So you have additional degrees of freedom when you have a diatomic gas. You have 3 for translational motion, like around in 3D space, and then you have 2 for rotation. So your diatomic gas can rotate about an axis like this or like this, which gives it 2 additional degrees of freedom. And then you have an additional 2 degrees of freedom for vibrating. So like they can vibrate towards each other or away from each other. So that's 3 + 2 + 2, which is 7. So in that case, the kinetic energy of that gas is 7/2 Boltzmann's constant times temperature. So while the kinetic energy of that gas is still related to the temperature, it is greatly modified by the allowable degrees of freedom, by how that gas is allowed to move. So there are 2 things I want to point out here. This relationship between kinetic energy and temperature is modified how particles are allowed to move, meaning what states they're in. Do you have a nitrogen gas or do you have an N2 gas? Are they vibrating? Are they not? Where are they located? Are they allowed to move throughout a box or are they not? And the second thing I want to point out here is that the relationship between kinetic energy and temperature is greatly modified by how the particles are allowed to move, meaning the probabilistic nature of what the velocity of those particles is. I had a little average over my velocity because I was like, oh, all the particles, we'll just take the average of all the velocities. But what does that mean? There's a very famous distribution called the Maxwell-Boltzmann distribution, which describes how velocities in an ideal gas are spread. And if we take the average, we get the most probable velocity. But that's probabilistic. The velocity of individual particles could be very high or very low. It's just that they average to some value. So if you're taking the temperature to be a relationship with the kinetic energy, but you're averaging over this huge system of particles, that means you don't really know the velocity of each particle. You're just saying the most probabilistic velocity is this, which is really interesting. When we study an ideal gas, for example, and we say, what is the temperature? We don't really know what the individual molecules are doing. So I find this to be a really interesting property of thermodynamics, where they say, well, we can't know the individual temperature of an atom, but we use the idea of a number density of atoms to say, well, this is the temperature, because this is the most probabilistic distribution of velocities. And from that, they get a pressure, and from that, they get an energy. Thermodynamics is the introduction of statistics to physics, saying we can't know what each atom is doing. And you also have to remember, at this time period, there was debate about whether atoms even existed or not. The existence of the atom was proven by Einstein with his 1905 Brownian motion paper. And before that, there was like big debate in the community. So you have people like Boltzmann. They're saying, we can't see these atoms. But when we talk about the number density of atoms and states, we get really good agreement with our measurements, and it makes perfect sense for what we're observing. And look at the stuff we're doing with the periodic table. It seems like the weights of molecules are exact like ratios of each other, as if the building blocks only have one type of mass. Isn't that interesting? And then you have people like Mach who are like, well, we can't see them. If we can't see them, they're not real. It's okay to use it as a tool to calculate things, but we shouldn't go around saying these atoms are real. And you know, what a time to be alive. What a time to be in physics. And it's so interesting that this discussion comes from thermodynamics, which to me seems like the most tactile and physics of all the physicses. Do you know what I mean? Like, you can build an engine and you can watch it do work and you can measure that work and you can look at how the energy is moving around, and that's thermodynamics. But they're using this as a tool to study the most basic building blocks of matter, and that's so interesting. And think of the two big names of thermodynamics. Maxwell does his study of heat, and then he goes on to be like, oh, and here's all of electrodynamics, no big deal. And you have Planck, who does his study of heat. Planck is actually really fun. He's like, the only definition of heat is when you rub your hands together. Heat produced by friction, everything else is energy. And it's such a weird distinction to make, and I love that for him. But Planck studies thermodynamics, and then he goes on and he does the quantum, all the quantum stuff, the quantum, you know. The building blocks of all of physics are people talking about pressure and temperature. It's really cool. Speaking of E&M, though, a second way to measure temperature with electricity. So in 1823, this German guy Seebeck observes the relationship between electricity and magnetism and heat. I don't have a thermocouple to show you. You've probably seen these before. You usually have two leads, and they're made of two different metals, and you have an open circuit, and you stick both of these into the thing you want to measure, and that causes an EMF voltage to go across the circuit, and you can measure what that voltage is, and that will directly infer what the temperature of that thing that caused the voltage is. So now they look something like this usually, and they will have a software in there to calculate what the temperature is. So the user doesn't really know about the EMF voltage thing happening. They're just reading the temperature. Something very similar also in 1821 by Humphrey Davy is the RTD, resistance temperature device. And I keep calling them RTD devices, and I'm so sorry. And it's just this discovery, the resistance of a metal is dependent on temperature. So if you stick a piece of metal in the thing you want to measure, and then you put a voltage across of it, and you calculate the resistance, you have this software that has some sort of fit to whatever the metal is, tell you what the temperature is. This type of thermometer is an RTD device. These were not in great use until they were able to be manufactured in the 1900s or so. But what I find interesting is that unlike the bulb thermometer, which is like a measure of collisions, this, like, someone in a lab took the nickel or whatever metal is in this and just got a bunch of data on how the resistance of this metal of a certain size changes with temperature. And that was put into some sort of fit, which is now a little software program that is inside here. And you measure your resistance, not your temperature. You measure your resistance, and then the software puts that on the little plot and gives you an approximate temperature. But you're not actually measuring the temperature. You're measuring a voltage, right? Isn't that kind of weird? You're not actually measuring temperature with this. You're measuring something that we say is related to temperature. And I mean, it is, because we've demonstrated that in the lab. This is a meat thermometer. It works the same way as the butt thermometers. The thing, we did RTDs. There's also the thermistor, which was our boy Faraday in 1833. So Michael Faraday found that silver sulfate, when heated, shows a huge reduction in the resistance of that material. So this is the very first observation of a semiconductor, whose applications, of course, explode, also in the 1900s. All three of these things, this relationship between electricity, magnetism, and temperature, is the most common way, I would say, we measure temperature, which again is interesting because you have to stick this into your thing you're measuring. You interact with the thing you're measuring to take temperature, and you're not even really measuring temperature, you're measuring a voltage or something. That's interesting. At least to me, I think it's interesting. All right, here's the ice cube update. You see that one's much shorter because it's melting faster. This is also interesting to me, but like, whatever. Obviously, these devices are good for specific temperature ranges, so the material you use would change based on your application. And another thing about these, if you're doing like really serious lab work is that they will degrade over time. They will become less accurate. So you also have to think about that if you're running a big, giant, expensive experiment. I did this video about thermodynamics a while ago, and in it I talked about entropy, and I gave this really annoying definition about how it's like the energy that's lost in mechanical work, and it's about the second law of thermodynamics. You can never make a perpetual motion machine. And I think in that video I was like, entropy in thermodynamics has always confused me, which is a true fact, but it makes more sense in statistical mechanics. So now I would like to talk about entropy in statistical mechanics, because you can't get to temperature in statistical mechanics if you don't talk about entropy. So there are many different ways to talk about entropy, and all of them are correct and in agreement with each other, but it just takes some flexing and work to get yourself to understand them that way. So I'm going to talk about entropy as in the number of states of a substance or a system, but I'm also going to talk about it as a measurement of disorder, because I think that visually is very easy to see. The second law of thermodynamics says entropy has to increase in a closed system. So if you imagine you have a box of gas and you've made it so all of it is in the corner, and then you remove some partition, what's going to happen? Well, the gas is going to fill the volume eventually. It is going to go from an ordered state where it's all in the corner to a more disordered state where it's spread across the whole volume of the box. That is one way to describe entropy. So keep that in mind as I tell you Boltzmann's definition. Boltzmann says entropy is a measure of the number of microstates in a system that constitute the macro state of that system. This is equivalent to the disorder thing, but I don't know if I'm a good enough science communicator to convince you of that, so it's left as an exercise of the reader. Here is Boltzmann's favorite equation, which was never written down by Boltzmann. It's from Planck's paper, but it's on Boltzmann's gravestone for some reason. S, which is entropy, thanks Clausius, is equal to Boltzmann's constant, which he also never wrote down. He was just like, there's a constant, but he never calculated the value. Isn't that interesting? So S is equal to Boltzmann constant times the natural log of omega, where omega is just number of states, the number. And remember the second law of thermodynamics, which says that entropy is always increasing in a closed system. Remember the closed system part, that's important. Like, you can take two systems and put them in thermal contact, and the entropy of one can go down as long as the total goes up. So it depends on how you're defining things. But you have to remember a closed system. So we had our little box that showed us that entropy as disorder. Like, things are ordered, they will move to a state of disorder. But that example of entropy always increases also shows us how temperature moves. You have your box, it's small, the molecules are under pressure, they're moving very fast, the temperature is high. You remove the partition, entropy says that those molecules have to become more disordered. They will spread across the volume, which directly implies that the temperature will go down. Entropy is related to temperature. Entropy is a measure of disorder, which is easy to see in this picture, but it's also a measure of the microstates of the system. So what does that mean? So I saw this really nice diagram from hyperphysics where they're using dice to describe the idea of a microstate and a macrostate. So if you have two dice and you roll them, a macrostate is the total number of pips that result from that dice throw. So the minimum macro state is that, like, 2 pips, 1 on each die. And the maximum is that you have 12, 6 pips on each die, right? The most common macro state is that you roll a 7. And there are microstates that constitute rolling that 7. So a microstate of 7 is that you could roll a 1 and a 6, or you could roll a 3 and a 4, or you could roll a 2 and a 5. That is the most likely and most possible macro state. And there are a bunch of microstates within that. Boltzmann's principle says that all microstates are equally likely for a specific macro state. So if you roll a 7, you are just as likely to roll a 6 and a 1 as you are to roll a 4 and a 3. And because they are equally likely, They are indistinguishable. Of course, we can see the dice. But in real life, we're imagining a gas where we just stick a thermometer in and we measure a temperature. We don't know where each individual molecule is or its velocity or what it's doing. All we can observe are the macro states. So again, if we look in our box and our definition of entropy as disorder, we see the gas moving from the corner until it's spread throughout the volume. There are uncountable microstates. And by that I mean, like, one particle is here, and then in a different microstate, that particle is this particle. And in a gas where you have a mole, which is 10 to the 26 atoms in it, there is no way we could ever track all of those atoms. It's literally impossible to know which microstate that gas is in. But because of statistical mechanics, we can think statistically, and we can say the most probabilistic macro state is one of the many, many uncountable, impossibly large number of microstates that is the most disordered. So entropy is a measure of disorder. We know that this gas will move to a maximum disorder that it can. Entropy is also a measure of microstates. The most probabilistic macro state is the one with the most microstates. So entropy, S, is equal to Boltzmann's constant times the natural log of the number of states. The most disordered thing is going to be the thing with the most states. So how does this get us to temperature? Let's talk about temperature in statistical mechanics. So the most rigorous definition of temperature has nothing to do with the kinetic energy of the particles. It has nothing to do with an ideal gas. It is true for all systems. So look at this definition. Have you ever heard of the thermodynamic arrow? That is what temperature is doing for us here. This equation is telling us that a changing system will move towards a higher entropy. And to do that, it will move energy around in the form of heat. Imagine you pour creamer into coffee. You have the creamer at some T1 and the coffee at some T2. You add those two systems, now they're in thermal contact. The entropy must increase, disorder must increase, the cream will mix into the coffee, they will reach some new temperature. The increasing entropy leads to a reduction of temperature of the coffee and an increase in the temperature of the cream until they are a mixed, fully mixed system. The only way for that system of cream added to coffee to increase entropy is for those two things to mix and for heat to flow. It's intuitive. You don't have to know about all the quantum states of the particles in your coffee to know that the most likely macro state is that these two things mix together, because we know entropy has to increase. Looking at this equation by itself might not be intuitive, but just experiencing the world and like seeing how temperature flows in the world and how entropy flows in the world, I think it becomes a much more intuitive definition. And this is the most rigorous definition of temperature. And this applies to all systems, solids, gases, whatever. Of course, you can use this and you can use statistical mechanics to recover the ideal gas law, because that idea of the temperature of an ideal gas being related to kinetic energy is recoverable. That statement is still true for ideal gases, but this is the most rigorous definition of temperature. We did it. Statistical mechanics. Ice check. I don't know why I'm still showing this to you. You get it. You see the demo. You see what's happening. I just think it's fun. People always associate temperature with heat, but they're different things. And the rate of change of a system is going to depend on so many variables, not just the temperature of the room. See that boy? He's melting. He's melting deep, deep down. It's going to make a mess. It's fine. I like it. It's fun. Okay. I don't know if you guys got the whole macro state just from the dice. So now let's do some quantum temperature stuff. Have you ever heard that a single atom cannot have a temperature? That doesn't really make sense from the kinetic energy definition, right? Like, I don't know, mathematicians, let me know. Can you take an average of one thing, or is that like not allowed mathematically? I would totally do it. That seems fine. You have one atom. The average kinetic energy is just whatever the kinetic energy of that atom is, and that's the temperature from the ideal gas thing. Like, that's fine, right? But you learn in 8th grade or whatever that temperature for a single atom is undefined. So let's look at that with our statistical mechanics definition of temperature. Imagine you have one atom and it's in its ground state. So it's just vibing at some energy level. How many microstates are available for this atom? Well, an atom in the lowest energy state can only be in one state, just that one. So omega is equal to 1. So remember, entropy, S, is equal to Boltzmann's constant times the natural log of omega. The natural log of 1 is just 0. So when you go back to our definition of temperature, it doesn't matter what energy that little atom is at. Like, it can just be some number, whatever, it doesn't matter. What you end up getting is 1 divided by 0, which is undefined. So that ground state atom, one little guy, its temperature is literally undefined. It doesn't have one. It doesn't make sense to talk about the temperature of that little guy. But we want to add some energy to the system. So we have our brick of energy and we break off one quanta, which we're allowed to do because Planck taught us that energy is quantized, and we shove it into that little hydrogen ion, and it jumps up to whatever n equals 1 energy state is there. So now we have one hydrogen ion at some higher energy level. How many microstates are there? Still just one. There's still just one. So again, you get that the temperature is equal to 1 divided by 0, which is undefined. One atom literally cannot have a temperature. But what if you had two? What if you had two little guys and they had the lowest energy state? Well, it's probably something like they're on top of each other and one has a spin up and one has a spin down, right? Except this has two possible microstates, because if you could paint particle A red, the red one could be up or it could be down, right? So you have two possible microstates. So when you do your little S equals KB natural log of 2, you get a number now, and you can get a temperature. And if you added energy to that system, one of those would bump up to the next energy level. And now you have 4 states, I think, because this could be up or down, this could be up or down, this could be down here. Is it 8? It doesn't matter. There's more. It's a bigger number. The temperature goes up. So it makes sense to have a temperature for a system of particles. It doesn't make sense to have the temperature for one little guy. But something else interesting about temperature is that this whole little idea of microstates and like probability and entropy increasing really only applies to things in local thermal equilibrium. So if you have a real nasty mess, it also doesn't make sense to calculate temperature there. Because if things are in the process of moving around so much, like imagine like a hurricane or like a vortex where you have like really weird chaotic dynamics, like unpredictable motion. You can't really determine what microstates are possible. So again, you're just going to get an undefined temperature. And that's kind of interesting too. For most purposes, especially in the world around us in labs on Earth, you can just assume local thermal equilibrium. I do it all the time. It's fine. You're allowed to do that. But I do think it's interesting that you do have these systems where temperature just doesn't make sense. Of course, there are these really interesting cases where you're not in local thermal equilibrium, and it would be really interesting to talk about, like, there's no temperature here, but how can you study the system? But that is way beyond the scope of this video. So let's talk about negative temperature. I'm going to show you a plot here, and it looks like a little hump, okay? Now I'm just going to, beside that plot, make an imaginary particle setup for us to explore. So imagine you have 10 particles, and they are constrained in a way that is not allowing them to move, so they have 0 velocity. That's fine, right? Because they still have some sort of energy. That's Planck, right? It's like n plus 1/2, so you still have energy. Imagine you force them via lasers and magnetic fields to all be spin up, okay? How many microstates are there? Just one, okay? You have one microstate because all of those have to be up. That's this little point on this graph right here. Now imagine you want to move up this hill. You want to move to something more disordered. What can you do? Throw some energy and flip one of those guys down. You can't see the particles. You don't know which one is down. So how many microstates are there? Like 10, right? Because each one of them could be down. You don't know what. Add some more energy. Now 4 of them are pointing down. Oh my gosh. How many? A lot of states. A bunch. Which 4 are down? You don't know. Now add some more energy. Half of these guys are spin up. Half of them are down. This is the most probabilistic state for these to be in because this has the largest number of microstates. If you had plotted the temperature of this situation to match this graph, you would have seen the temperature going down as you move to more disordered states. Just like if you release your gas into a bigger volume and it spreads out. The temperature has gone down. But you're at the top of this curve. You can see people are doing something else. What if you flip another one? And so now you have 6. Oh, I forgot which way I was going. They're all going down, right? So now you have 6 down and 4 up in the opposite way. You've reduced the entropy. You've made it less disordered than it was before. And of course, you're allowed to do that. The system, the universe has to increase in entropy, but you can do work on this little system of particles by shoving energy in. It just has to come from somewhere. That's okay. We're allowed to do that. And you keep doing it and you keep doing it until now they're all down instead of all up. If you plotted the temperature of this system, it is now in the negative. And this is a real thing people can do with like lasers and magnetic fields. But I don't think this is that interesting. This is like the type of YouTube video you would see with an AI voice and an AI picture of Brian Cox. Like it's just, this is a thing that's technically possible, but it's like a loophole in the definition of temperature and not really a negative temperature. Like if you think 0 Kelvin is the lowest possible temperature, I mean, if you think that, like it's defined to be, I'm sorry, it's defined to be that. I don't know why I gave you an out to say you don't think that. It's defined to be. Negative temperature does not mean it's going below here. It's just that the thermodynamic arrow is pointing in the opposite direction. You're like shoving energy into it. And while I would be very interested to someone who does that experimentally tell me how they did that with the lasers and the magnetic fields, like as a concept, it's not that interesting. Like, oh, you found a little quirk of the definition. Okay, so instead, let's talk about something that's actually interesting, which is plasma. Okay, cool thing about plasma, that's like a definitive thing about plasma, is that within a plasma, there are multiple different species of things that have different temperatures. So you'll have an ion gas, and you will have a neutral gas, and they interact via collision stuff. But on a larger scale, these two gases, they overlap spatially, but they are not in thermal equilibrium with each other. They are in thermal equilibrium with themselves, so they each have a temperature, but they are not given enough time to interact to come to some full equilibrium. So you can literally measure the two temperatures of the two separate gases in this one single thing. The timescale of the ions interacting with the magnetic field is so much shorter than the collision frequency that they just don't join together. And so you have two temperatures. And that's really interesting. So one more aside. How do you measure temperature? Number 3, I think. We're on 3. Blackbody radiation. Okay, here's Planck's boy. Look at his little equation. Look at this little plot. Look at these stars. Stars are plasma, right? How can you tell the temperature of these stars? You look at the color. So now, for the first time, we have a way to measure the temperature of something without having to interact with it. It's not like you can just throw a thermometer into the sun and measure the temperature. That was a joke because they did that. They did that with the Parker Solar Space Probe. It's still going around. It's still doing it, but I just think it's really cool. They did, in fact, throw a thermometer into the sun, and they got the data back. So deal with that. That's really cool. But you don't have to, because you can use blackbody radiation. So the temperature of a body will be directly related to the peak wavelength that it gives off. You can measure the wavelength of those photons, and you can say, that is the temperature. That's how these guys work, right? You see? Yeah, and you measure the temperature. It says I'm 90.1 degrees, which feels wrong. And this is kind of it for me. This is the most exciting way to measure temperature, because you don't have to stick anything into your whatever you're measuring to get a measurement. You don't have to interfere with the thing you're looking at to measure the temperature of that object. There is, of course, some problems. This is actually a very active field of research. These things, they only measure surface temperature. And also, most things are not black bodies, Like the human body is close to a black body, and it will reflect that wavelength in some infrared temperature, but it's not perfect. There was a couple interesting studies because of 2020 when everyone was using these to determine if melanin, like your skin color, changes the amount of emissivity, like how much light will be reflected, which would mean that if you have a lighter skin color, the thermometer would read higher than if you have a darker skin color. But I don't think it does. I think humans have the same emissivity about no matter what their skin color, which means these things can actually work and be pretty accurate, even though usually when you go to the hospital or something, they do like the mouth one or the butt one if you're unconscious. Because that's more accurate. But I think it's interesting because how to measure temperature is a very active field of research. Like, if you imagine you're building a satellite for NASA and you need that material to withstand the super high temperatures of like re-entry. So you want to very specifically melt that material to see at what point it melts. You need to very accurately measure the plasma or the fire, whatever you're making to melt that thing. But you can't just shove a thermistor in there because those will melt. The metal will melt. So how do you do it? You have this really hot flame and you measure the wavelength off of it and you determine the temperature. But it depends on hundreds of things. It's not as easy as like looking at a sun and being like, I'm an astronomer, it's blue, and say within an order of magnitude what the temperature is. You need a very specific number. And thermometers melt and they degrade over time. And surface temperature is not the same as the actual temperature inside the material, and you don't know what the emissivity of all the materials are, and you have to do all these tests, and it's a super active field of research. Measuring temperature is not nearly as easy as you would expect it to be 400 years after the invention of the thermometer, especially now that our rigorous definition of temperature requires a knowledge of the quantum states of the material you're looking at, which is just not available to us. It is not analytically available to us to calculate the quantum microstates of macroscopic systems. That math is beyond us, just a numbers wise. We cannot do those calculations. So it's a lot harder than you would think. And people kind of move back to those 1800s, like, well, we'll just test it. We'll just measure it. We'll just do it 400 times. We'll make a plot. We'll extract a fit. And that's the emissivity. see? It's melting much faster than this guy. I did a physics demo. This one worked this time. Nice.